I'm going to be off camera and not visible the entire time because I'm never shouldn't be speaking. But if anyone needs me for anything, you can just send me a direct chat message. I'm definitely here listening, and I'll also put through that link for attendees when we get to Nancy's talking about MSEC. So I'm on it. And Barbara, I'll just mention right before I do press that start webinar, although I think you can probably tell when I do, but I'll let you know.
Thanks. Appreciate it.
Of course. I'm just going to put a spotlight on you right now. And then when I remove that, all right. Okay. All right, I'm going to start.
Hello, everyone. Thank you for joining us today for ASME's Tech Talks. I'm Barbara Slotnick, Senior Manager of Tech Operations at ASME. These talks are a monthly one-hour webinar series focusing on topical subject matter in a variety of mechanical engineering disciplines represented by ASME's technical divisions and technology groups. Before we get started, I'll mention that we have time for Q&A after today's talk. If you have a question, please type it in using the Q&A icon in your Zoom screen, and we will do our very best to get to as many as possible. Now it is my pleasure to introduce Monir Halou with the University of Maryland, who is the chair of the Manufacturing Engineering Division Executive Committee. Monir, take it away.
Thanks, Barbara, and thanks everyone for joining today. It's my pleasure to welcome you here to today's Tech Talk. Before sort of kicking things off to our speakers and introducing them, just wanted to give a little bit of background and context about both the MED and the Women in Advanced Manufacturing Forum. So Manufacturing Engineering Division at ASME, we're very much interested in the science and technology of improving the performance of processes and systems that are basically making products as the desired end result. We've been doing this now for 101 years. We were very pleased to be able to celebrate our 100th anniversary last year with ASME's help as well. And we're hoping to be able to continue on into the future, providing great topics here and really focusing in on some really cool research, technology development, and innovation. One of the things that we're very keen on here is to broadly engage our community, really try and promote efforts to bring in new voices, underrepresented individuals, and new ideas into the community and into the discussion. And it was with that in mind a few years back, with the support of a TEC Development Fund award, we were able to kick off the Women in Advanced Manufacturing Forum to provide a place for us to bring together, again, underrepresented voices into our community and really highlight the great work that's going on there. And so with that in mind, it's my pleasure to introduce Professor Nancy Diaz from the University of South Florida, who is the chair this year of the Women in Advanced Manufacturing Forum. Nancy, over to you.
Thank you, Monir. Welcome, everybody. Thank you for joining us today. This Tech Talk has been put together by the organizing committee of ASME MED's Women in Advanced Manufacturing Forum, who we have the pleasure of joining us today online. Our third annual WEAM Forum will take place in June at the ASME Manufacturing Science and Engineering Conference to be held at Purdue University. Everybody is welcome to attend. For the WEAM Forum, we're very excited to bring forth an expert panel from industry, academia, and the government on smart manufacturing. to discuss their vision for enabling Industry 4.0 in the manufacturing sector and transitioning to Industry 5.0. In addition to our networking event, we have a workshop on reimagining your career. Will be hosted by Tara Winston of Intract Consulting. I would like to give a special thanks to our gold sponsors for the WIAM Forum ASME and event. You are more welcome to join us. You can visit our website at the MSEC page, which will be shared via chat. And now it is my pleasure to introduce you all to our speakers for today. So today we'll be focusing on opportunities and challenges for innovative metal manufacturing in the automotive industry. We'll start off with Dr. Whitney Polling. Dr. Polling holds a Bachelor of Science in Material Science and Engineering from Washington State University and a Master of Science and a Doctor of Philosophy in Metallurgical and Materials Engineering from Colorado School of Mines. She joined General Motors in 2017 and is a senior researcher in the Additive Manufacturing and Electric Motors Research Group. Her research focus areas include micro X-ray CT for porosity characterization and tensile and fatigue behavior metals, laser powder bed fusion additive manufacturing, as well as process structure relationships of automotive alloys. We will also be joined by Dr. Ala Qattawi, who is an assistant professor in the Department of Mechanical, Industrial, and Manufacturing Engineering at the University of Toledo. She received a PhD in automotive engineering from Clemson University of South Carolina in 2012 and became the first woman in the United States to earn a PhD degree in automotive engineering. So we're very fortunate to have her here with us today. Dr. Qattawi's research interests include advanced manufacturing, additive manufacturing and sheet metal forming, design for manufacturing, intelligent manufacturing, and origami-inspired metal structures, as well as applications in vehicles, body and light design. And without further ado, Whitney, I will hand it over to you to begin.
Thank you very much, Nancy. It is my pleasure to be here today. Thank you so much to ASME for giving me the opportunity to share this work with you. I would also like to thank my fellow colleagues here at General Motors Global R&D who contributed content to this talk today. So the core of additive manufacturing at General Motors is the Additive Industrialization Center. This is located here at our Global Technical Center in Warren, Michigan. It is a facility that has 24 polymer and metal 3D printers. Most of those are polymer printers. And our R&D lab opened in 2018 with 2 metal laser powder bed fusion machines in order to support the broad implementation of metal additive manufacturing within General Motors. In terms of the history of AM at GM, polymer additive manufacturing has been used for rapid prototyping for several decades. And in fact, in just the past decade, over 250,000 prototype parts have been produced for the company. So additive manufacturing is a really important process for our business at General Motors, and there are 3 main application areas. So the first being functional prototypes. So these are prototypes that are put onto vehicles during the development process, and they undergo a variety of testing. The second is manufacturing tooling. So this allows us a rapid response solution to challenges that arise in our plants. And finally, there's product. So these are examples of parts that are going on our 2022 Blackwing V Series Cadillac vehicles, and most of them are polymer parts, but we are starting to incorporate metal AM parts. You can see that there's an inlay medallion on the mechanical shifter knob. So in terms of metal additive manufacturing, we're trying to implement it more broadly within the company. We have a long history of polymer AM, but there are some significant challenges that come with metal AM. But we are looking forward to the future and brainstorming ways that metal AM can be a game changer for us in the automotive industry, especially with respect to low volume manufacturing. So this is an example. This is more of a thought experiment with Autodesk, where we went and took a seat bracket and came up with an additive design for it that consolidated 8 components down into one part. And this design is in theory 40% lighter and 20% stronger. So we are really looking for new ways that metal additive manufacturing can enable new opportunities within the business in the automotive space. Some of those hurdles that we need to overcome to broadly implement this manufacturing technology, I have listed here. So I've summarized it in terms of materials and manufacturing challenges. And the bullet points that are highlighted in the blue boxes are areas that I'll touch on in the talk today. So in terms of materials, we see a need for more automotive grade agnostic alloys. So this means that we're looking for alloys that are low cost and that can be produced at quite high volumes for automotive needs. These are things like low alloy steels, tool steels, aluminum alloys, and copper. On the manufacturing side, we have a significant need for increasing the speed of metal additive manufacturing and producing at much higher volumes. So for example, if we're trying to produce production parts, a low volume vehicle program might be 4,000 to 6,000 vehicles per year. We are also facing challenges at the moment with part and process repeatability. So how do we get the same part every time that we print it? And additionally, it's also really critical to us to have minimal post-processing of our parts. Post-processing incurs extra time and cost. And so we are working really hard to try to keep post-processing to a minimum. So today I'll be focusing on laser powder bed fusion. If you're not familiar with this process, the video shows you the basics of it. So a spreader will spread a thin layer of powder across the powder bed, and then the laser will come through and melt the cross section of the part for that specific layer. These layers are roughly on the order of 50 microns. Sometimes they can be less, sometimes they can be greater. And that means that for a given part, we could be dealing with hundreds or even thousands of layers built up to build the entire part. So when we first started looking at laser powder bed fusion several years ago as a possible manufacturing method within the automotive space, we went out and obtained samples from several commercially available alloys that were out there. Stainless steel alloys were the most common options in terms of steels at that time, several years ago. And then we also had 4140 samples printed because that's closer to an alloy that's more commonly used in automotive manufacturing. And what we did was we had these samples printed with external suppliers, and the porosity came out looking really good in these samples. So there was less than 0.5% porosity in them. And we heat treated them using heat treatments that we typically use for wrought products. And then we compared the results. And what we found is that in general, the tensile properties were excellent for these low porosity samples. So for the stainless steels, we had heat treated them according to an ASTM heat treatment standard, and the strength values exceeded the minimums called out in that standard. And for the 4140, the tensile properties were comparable to wrought properties reported in literature. So this is a great result. This tells us that we can get great mechanical properties in terms of static tensile properties from parts that are produced with metal AM. And we can utilize them for applications where it's a stiffness-driven design. However, there is some porosity in the part. In the automotive space, we choose not to use hot isostatic pressing as a post-processing step. That step is used in other industries to reduce or to try to eliminate a lot of the porosity that's inherent in laser powder bed fusion parts. But for us, it's just not feasible in terms of the amount of time and the cost associated with it. Therefore, we are dealing with some amount of porosity, even if it's a small amount in our parts. And this is very detrimental for fatigue. This is a huge concern for us because there are a lot of parts in the vehicle that undergo fatigue loading. And the porosity within these AM parts leads to fatigue crack initiation at the pores. And you can see from the plot that the fatigue strength is reduced. So for these experiments, we looked at a range of alloys, so aluminum alloys, titanium, and some steels. and they had a wide range of porosity, from the steels having very low porosity, less than 0.5%, all the way up to some of the aluminums had around 5% porosity. And across the board, across all of the alloys that we tested, essentially the additive samples had fatigue strengths that were on the order of cast samples. And both the additive and the cast samples had fatigue strengths that were quite a bit lower than wrought samples. Typically for additive samples, the fatigue strength to yield strength ratio is about 0.3. For wrought samples, it's roughly around 0.5. And so this presents a significant challenge. This is something really important that we need to consider when we are looking at, should we use metal AM to make this particular part for an application? And how do we design around the porosity? So after we surveyed the commercially available alloys, we kind of realized that there was a need for some alloy development. We were looking for alloys that were low cost, meaning very low alloying elements added to them. And we needed them to perform for specific automotive applications. And we also wanted to design the alloys to be printable. So they were designed for the laser powder bed fusion process. And so this is example data from some of our efforts with designing a high strength aluminum alloy. And at room temperature, it well outperforms the aluminum silicon 10 magnesium alloy that's very common in the additive space. And it maintains a slight strength advantage with elevated temperature as well. So it's applicable to a wide range of applications in the vehicle. Additionally, it also performs well in terms of fatigue strength compared to the ALSI 10 magnesium. We are also looking at designing steels. The example shown here is a custom low alloy steel. A lot of the alloying elements were removed. This is kind of a bare bones alloy that we can use for a variety of applications. And it has lower strength compared to, for example, the 4140 and the precipitation hardenable stainless steel. Something interesting that we found though when we did the fatigue testing was that the fatigue strength to yield strength ratio was around 0.4. And for all of the previous alloys that we had tested, it was around 0.3. So this was a really interesting result. And so we are doing a deeper dive on it. We believe it's related to the complex microstructure of this alloy. And so that's kind of where we're going with alloy development. And when we think about printing the parts, I mentioned before, it's critical that we have minimal post-processing. It's already a fairly time-intensive and costly process to produce parts with metal additive manufacturing. And so we essentially want the parts to be as close to the finished product as possible when we pull it off the build plate. One important consideration for that is the dimensional performance of the technology that we're using to build the part. And so the examples shown here are geometry features from the ISO ASTM standard that was developed for additive manufacturing. And we print these features with a wide variety of metal AM processes. And we also compare machines from different suppliers. And we also look at it to compare how different alloys print and what happens when we change parameters. And so you can see from the data set here for these resolution features that we can get measurable differences, even within laser powder bed fusion for parameter sets that are well known for stainless steels. So this is the linear artifact. We got some interesting results for this when we looked at how the custom low alloy steel printed compared to stainless steels that are widely commercially available. So for this artifact, the average deviation of the 5mm cubes on it was significantly higher for our custom low alloy steel compared to how the stainless steels printed. This ended up being a significant result because it resulted in machining challenges later on. We were building parts that had some tight tolerances in certain areas, and we actually needed extra machining stock on it. So dimensional performance is really important to us when we're looking at metal AM technologies. And finally, there is also an artifact that's called out in the standard for printing overhanging angles. And this is really interesting because it allows you to quantify the change in surface roughness with decreasing down-facing surface angle. And so surface roughness tends to increase with decreasing down-facing surface angle. And this presents a challenge to us in terms of post-processing, because if we have a complex part with a lot of different down-facing angles, it means that we're going to get a variation in the roughness across the part. And so if we need to do some sort of surface machining on it, that presents a challenge. And how do we get a uniform surface finish? So these are all challenges that we are addressing currently in terms of post-processing. I mentioned also that in the automotive space, we're really concerned about increasing throughput. So we need to print parts much faster and we need to print a lot more parts. And this data set is an example of one approach that we've taken to try to improve throughput. Now, this was a low-hanging fruit. This was simply working within the parameter space and seeing how we could speed up the process. So the example I'm showing here came out of parameter development work that was done on our custom low alloy steel developed at GM&D. And what we found is that within the parameter space, there were ranges within the parameters that gave us these parameter development cubes that had fairly high density, so over 99% dense, but the parameter ranges were quite wide. And when we looked at how long it took to print the cross-sectional area of these cubes, the difference in time to get these high density cubes was ranged from about 1.5 seconds to about 3.5 seconds. And that doesn't sound like much when we're talking about a small cube, but when we're trying to print an entire plate of parts that might be thousands of layers tall, this can actually turn into hours of time or even days of printing time. And so this is just one example of one of the ways that we are going after throughput. And it shows you an example that we have to consider throughput really in every aspect of the metal additive manufacturing process. So I mentioned previously that we are not pursuing HIP as a post-processing step. So that means we're accepting some level of porosity in our parts. So a critical part of our research work here at GM&D is to understand this porosity really well and how it impacts properties, not just mechanical behavior, but we're also concerned about things like thermal conductivity and electrical conductivity for some of the applications within the vehicle. And so the examples shown here show parts that were printed that are over 99% dense, but there's obviously a significant difference in the porosity in these parts. There's a difference in the morphology. So we have keyhole porosity in the center there, and on the right, we have lack of fusion porosity. So it's these large, jagged morphology of the pores. And also there's an interesting distribution in the porosity. So with the keyhole porosity, we have these clusters of pores, and there's also a periodicity to the porosity clusters within the part. And so these are really, really important factors to understand when we're printing parts, because this porosity will be present and we have to incorporate that knowledge into our part design. And so I wanted to leave you with some final thoughts. So for additive manufacturing, we do utilize it quite a bit in industry. It's really important across a broad variety of applications, including functional prototypes, manufacturing tooling, and production parts. But we see the need for significant cost reduction and throughput increases in order to more broadly implement metal AM within the company for automotive applications. At this time, we're pursuing automotive alloys that are cost-effective, are high volume, and meet automotive needs. And we found so far that we can get some excellent results in terms of the tensile behavior, but other properties can be substantially impacted by porosity, such as fatigue. Some areas that we've identified for development include in situ process monitoring, material specifications, post-processing techniques, and part quality and repeatability. So I'd like to thank you so much for listening to my talk today, and it's my pleasure to be able to hand it off to Ala now for her portion of the talk.
Thank you so much, Whitney, and thank you, ASME and Women in Advanced Manufacturing for this opportunity. Moving or shifting gears to a new manufacturing process that's innovative, we will talk about origami sheet metal folding, or what we abbreviate as OSM. This is a part of ongoing research, and thanks to my PhD students, Mohammed Ali and Aladdin, for contributing significantly to the research that I'm going to show today. So the first that comes in mind when we talk about origami sheet metal folding is it basically what it is. So there's a specific type of origami called rigid origami, where we basically look at thicknesses, basically more than the paper thickness, and fold over the edges or the fold lines of a certain shape. Now, when we apply this to automotive structures, what that means is that when we design our sheet metal product, we will have a flat pattern that's 2D, and then we try to create the 3D component by sole bending. So this will be, all faces will be connected somehow, and then we fold them to the required shape or 3D geometry. The process is significantly depends on what we call material discontinuities, and you can see them here. The material discontinuities is a form of a deformed or removed material along the bend line. So the figure here shows material discontinuities that are laser removed, but we also can do stamped material discontinuities. And then as this process indicates, this requires a lot of design and basically thinking the process through while we're designing the 3D part. So because it depends on material discontinuities distribution along the bend line and where they are and their shapes. There are various topological entities that we can call MDs that can effectively be produced on the fold line to create a 3D geometry, and they're significantly different in their mechanical behavior and response after folding. So why origami sheet metal folding is an opportunity for innovative manufacturing processes? The reason for that is the less likely need for a die or basically a high presses that can form the part. So the part that you see here is actually folded in the lab by hand. We just needed jigs and fixtures and basically tables to fold this component with a careful design, of course, of the laser cutted material along the bend line previously in the flat sheet state. There are various components or various methods we can call within the origami. So the one that I mentioned is about material discontinuities. And there's also another collaborator in Aachen University who are, they are doing a different form of origami, but it is formed with 90 angle degrees components. So the component you see here is a structural body in white component that goes into like post office vehicles in Germany. And it's slowly done by folding. So they didn't need any dies or bends or dies or molds to form the bends. The next question that comes into mind is where we can apply this, right? In a vehicle, in a body in white structure. And there are various components that we can apply, mostly that are under the hood. So they are not class A surfaces or the closure panels. Examples that can be that the floor panel with the dashboard and the center console underneath structure. We can have a shock tower, and also we can have cross-member structures with combined folding lines under the hood with careful design for the origami requirements. So why we use origami? Why we basically petition for origami to be an innovative manufacturing process in sheet metal manufacturing for automotive structures? There are potential for origami when we look at it from component and manufacturing wise, stepping away from the paper world of origami. So the components, basically, if we look at the flat pattern of the floor panel that I show, we can consolidate components. And this means less joining and processing operations, post-processing operations that required for a single component made by origami sheet metal folding. We can also enable flexibility on the production line by having a one-piece flow. So this is a whole consolidated component that moves into clusters that enables us to better design the production line for the sheet metal. We can also eliminate the need for rigid tooling dedicated to each component because basically if we can create the component without the need for stamping dies that produce the curvatures and the edges, this enables us to have minimal tooling costs for various shapes and components that we can create. And if we carefully design the component with the required MDs, with their mechanical behavior and the loading, we can also create angles and corners that basically avoid cracks and tears along the bend line with the right analysis and design tools. Now, if we looked at the process-wise, and we want to compare, like imagine that we're introducing origami sheet metal folding to a full production of stamping of sheet. So we know that the material starts with a rolling sheet from the mill. We do chemical treatment, we have forming, we store it in a certain of a curvature component, we apply adhesive bonding, we apply spot welding, and then basically we have the part in a required shape. We can do thermal curing for painting, and then we do assembly with the rest of the vehicle component. Now, introducing origami sheet metal folding to the production line can have shifts and changes and potential advantages where we can do that. So the first one is that we basically don't have forming presses. We can just have blanking operation and a laser cutting or a progressive stamping for the MDs that can produce various shapes, right? So it's not like about the die shape that gets the inverse shape of the sheet that we want. And then we can minimize on storage because these are flat patterns that are drawn on demand once we actually need them to hit the production line. We can also have a potential to do thermal curing and painting in the flat state of the sheet metal instead of having it in the curvature. Well, it's basically all, we have more complex requirements to satisfy for the thermal curing. And then we can apply laser cutting and then folding on demand and reducing in adhesive and bonding and spot welding operations. And we move on with the assembly of the required operations. Now, the question that comes into mind, if origami sheet metal folding is that great, why we just use it now? Why we don't have it and produce products by sheet metal folding now? The reason for that is most of the principles that we know about topological analysis and geometrical restrictions in origami comes from the paper-wise. And when we increase thickness, basically sheet metal thickness, there are more limitations and challenges we need to face. So the rigidity of the material, the geometry requirement, the manufacturing requirements and constraints that comes into producing sheet metal, the added thickness of the sheet, and then the loading and mechanical properties and behavior of the component that is produced. And those challenges can be solved in a multifold research problem, at least now, where we can tackle each of those items in order to facilitate using origami in body-in-white structures. So the first analysis when we talk about origami is how to go from 2D to 3D. So this is a challenging aspect because if we have a 2D we usually start with a 3D component in mind, and then we need to unflat it in order to see how we can fold this and what's the sequence for that. And that's what's referred to in origami as topological analysis. The topological analysis tool's beauty is that it doesn't take any thickness into consideration, at least at the first stage. And that's enabled us to twist and turn all these faces and bends in order to get the 3D structure. So we start with the component you see here, the one, and then we can end up with the analysis and the right algorithms with a flat pattern, 28 or 29 flat patterns possible to fold the component that you see in one. And all of those with the fold lines shown can be successfully folded into the required shape. The more faces we have, the more flat patterns we can produce. And as you can see, not all of them is, in manufacturing-wise is acceptable, because some of them extend in a one direction or basically have a lot of rolling lines. And the question that we try to answer in this research is how we can standardize the research or standardize the analysis in order to be able to get a CAD file, manipulate this CAD file in a computer program, and basically get the flat patterns. And this, what we do is using graph theory analysis, and the graph theory analysis advantage in this specific field is that it can take a 3D geometry, boundary representation of a component, put it into nodes, basically a network representation. And once we have it in this form, we can translate that into basically numbers, matrices that can be easily manipulated by a computer algorithm. And this is the advantage where graph theory analysis can be handy when we want to go from 3D to 2D analysis. So once we have all these 3D flat patterns unfolded to 2D flat patterns, this is where the origami or paper origami stops. The field of origami now cannot go beyond in basically realizing the manufacturing abilities. And this is where engineers need to be more involved in sheet metal origami, where we put optimization techniques that meets design for manufacturing, design for assembly, design for sustainability, and all of those are required when we look at an actual component that will go into a vehicle. So we can look at the flat patterns in terms of compactness, measure how the extension of those flat patterns and the inverse, basically trace back this to the bed or the machine beds that will handle these flat patterns in their flat state. We can also look at the optimality based on nesting efficiency. If we're doing this multiple times all the day, how many flat patterns can we cut out of a sheet metal strip? And then we can have optimality based on welding cost. If we induce a certain cost within the algorithm, we can also pick a flat pattern that will have minimal cost, basically minimal length to be welded, or minimal spot welds on a certain component, and basically promote this as our optimized flat pattern that will produce the part. So now if we have an optimized flat pattern and we can produce it in a production line, the next question that comes into mind is mechanical behavior. These are not just sheet metal components that will be for display. They will have loading, and crashworthiness analysis, all of those needed when we look at sheet metal structure, especially for the under the hood body in white component. And then we looked at the tensile and shear analysis of those MDs, especially for the laser cutted MDs along the bend line. And the interesting results that each MD, though they have the same amount of material removed along the bend line, they behave differently, totally different in shear and tensile. And we found MD topology that even do self-locking in shear loading, and that increase even the strength of the MD or the fold line during shear loading, which is basically can be further optimized for the MD to behave in a certain manner within the shear analysis if there's a shear loading under the fold line. We also looked at scalability, and what we mean by scalability is relating the MD geometries and topology to the sheet metal thickness and basically the fold line characteristics. So if I'm doing this with stainless steel, certain grade like grade 16 or 14, is this different if I'm doing this in aluminum with a different thickness? So all of this makes a difference. How big my MD or materials discontinuity feature will be if I'm doing this with any actual topology. And we did a parametric design analysis where we tried to correlate the MD geometry, so the width, the length, the separating distance, all of those features to the actual mechanical behavior in terms of shear and tensile loading for each MD to get an acceptable scale. So how big and small we can go, and the binding agent for all of the scalability analysis is the thickness of the sheet. After we get the right scale, that how big or small we can go for the MD, we need to look at the bending angles versus plastic strain. And we looked at the localized strain along the bend line, and with the objective of understanding if this MD will sustain and when it will crack after bending. So there are two types of strain that we investigated. The first one is strain due to induced bending while we're bending the material. And the second one is in the bending state and loading the component. You can see from the figure that the experimental and finite element analysis were basically confirming to each other up to the 40 angles, and then we started having a deviation between the experimental and the finite element analysis, where we see that the plastic strain is actually less, goes to less values when we go to 90 degrees compared to the finite element analysis. We also looked at the microscopy analysis of crack initiation along the bend line. And you can see that we tried to achieve very sharp edges or sharp bends along the MDs in order to see when is the crack will be initiated and what is the location within each MD topology is the high critical strain region that we need to look for and basically redesign or maybe make thickness higher for these MDs. When we compare this to the regular ductility fracture theories, we found that there are two trends for certain topologies of each MD. The first trend is a regular one, that the larger the curve to thickness ratio, basically the laser cut to the thickness of the material ratio, this is less likely fracture will happen along the bend line. And the surprising features that we found is that there is specific MD geometries that shows no changes regardless of changes in the curve to thickness ratio. And this is a good news for us because basically what it says that those MDs are not dependent on a scalability. So we can make them big or small, and then there's no crack initiation or any fracture that will happen along the bend line because of the geometry and the topological geometry of the MD. So now, with all those analysis and developed knowledge that we know about origami sheet metal folding, the next question is that why it's not commercialized yet, like why we don't use it in a full production for components. Unfortunately, with all these analysis that we have and knowledge we gained through the 10 years of researching origami sheet metal folding, there's no suitable way that we can take a ready 3D geometry that goes now into the car and basically put it into a software and say this is the this is the design for origami sheet metal folding. So origami sheet metal folding is not suitable for all 3D sheet metal geometries. And then we have a significant integration between the 3D design and manufacturability that's required in early design phase. So the way of thinking that needs to be done is when we design the 3D component, we design it for origami sheet metal folding. It's not that we take a part out of the shelf or from the records of OEM and we say, what about this component? Can we just unfold it and do it by origami? So there's significant 3D design that needs to be done at the earliest stage of the design of the component. And there are a lot of reshaping current part design in order to meet the origami requirements, especially if we have complex components that have a lot of curvatures and a lot of faces. It may not be doable to unfold that to very long flat pattern. So this is the challenges of origami sheet metal folding. Now, the future impact and potentials for origami sheet metal folding is that it changed how we think about sheet metal design and manufacturing. So when we look at the origami sheet metal folding, the advantages is that it's non-shape dedicated. So one press and one laser cut can produce basically any shape that we require. So there's no heavy investment in dies and molds to create different shapes. It also offers efficient approaches to evaluate material flow deformation. And I want to draw your attention to basically when we look at the tensile strength of a material and in the elongation that we can achieve. Of course, we want to have the highest strength of a material with the highest elongation that's possible for deforming. Origami sheet metal folding basically, since we don't deform the material in actual stamping, so we don't have a flow characteristics of the metal that needs to flow between a die and a mold, we can localize this folding or this forming of a material along the fold line. And that will enable us to use materials with high strength and maybe less than accepted elongation comparing to stamping. So we can increase the strength of the component, reduce its thickness without any disadvantage in forming capabilities. We can have better integration between design and manufacturing, especially for prototyping. Since we can prototype anything, we don't have to have shape dedicated tools. We just create the material discontinuities along the bend line with a careful design, fold it in by hand or with jigs and fixtures, and we can test how the components actually sound and look and where the welding will go. So with that, this concludes my presentation. Thank you for listening, and I will hand this back to Nancy.
Okay, and I'll hand it back over to Barbara.
Hi, everyone. That was fantastic. Thank you so much. We appreciate your time and sharing your expertise. Before we wrap up, I'd like to mention that if you are interested in obtaining a PDH certificate, look out for a follow-up email if you opted in to receive communications from ASME. If you have colleagues who were not able to join us today, this recording will be posted within the ASME members page for the Tech Talk series, typically within 1 to 3 business days. If you'd like to request a Tech Talk topic or provide feedback, a survey will appear in your browser window once this Tech Talk has concluded. We'd really appreciate your feedback. The next Tech Talk will be presented by the Tribology division, scheduled for Thursday, May 19th at noon Eastern Time. Additionally, if you are an ASME member and would like to join a division like the Manufacturing Engineering Division, visit asme.org and log into your account. Click on Additional Info, and here you can select up to 5 areas of interest by clicking Edit next to each technical division interest. By doing so, you become a member of these groups. Thank you again for joining us today. We hope to see you again soon. Bye for now.